Hello everyone, I am Lauren Wang from the Princeton HCI group. Today I'll be presenting our work, done in collaboration with X-OOHRI and Parastu Abtahi, titled Explainable HRI, Communicating Robot Capabilities and Limitations as Augmented Reality Affordances. Robots are becoming increasingly capable, but human users struggle to understand what they can and cannot do. Novice users may not know a robot's full capabilities, and when a task fails, they often cannot identify the cause. Consider a very simple example where a user asks a robot to rearrange books on the shelf. This small robot can pick up the book on the lower shelf, but the one on top is out of reach. Without any feedback, the user has no way of knowing why certain action fails or how certain instructions will be executed. This problem becomes more pertinent in even more complicated environments. Furthermore, robots' capabilities might change over time, and people's mental model needs to adapt as well. Prior work has tried to address this problem by providing textual explanations or prompting a robot to ask for help. However, language can be ambiguous. We propose Explainable Object-Oriented HRI, an augmented reality interface that communicates these missing information in situ. When an action is not possible, we surface the constraints and provide resolutions. When an action is possible, we visualize the instruction in a simulated environment. These AR visualizations form an explainable preview in real time, while users perform object-oriented interactions. Here's a demonstration of what the user sees in AR. When she attempts to move the book on top, she immediately sees that the book turns red, with a tag explaining that it's too high for the robot to reach. She then drags the book on the lower shelf and moves it to the place where she intends to put. The AR visualization here shows the simulated actions in situ. Now let's walk through the case of robot capability. In order to give instructions, the user has to first select an object. A white circle signifier at the tip of the controller ray indicates whether an object is actionable. Afterwards, the user needs to select an action. We set the default action as move, but robot can do much more, and those high-level or composite action possibilities are shown to the user via the radial menu. The user wants to move the book somewhere else, so she drags and drops it directly to specify the placement. To achieve this, we created ghost objects, which are life-size, world-aligned virtual twins of real-world objects that conforms to the environment. Once the user confirms the instructions, a robot will execute the actions. On the other hand, when a robot cannot take an action, we visualize the constraints and provide resolutions. We color-code the ghost object in red and attach an explanation tag that labels the constraint. This visualization updates in real time as the user interacts. You can see the red color coding disappear when the placement becomes reachable. Additionally, we provide resolution options to resolve constraints, and we visualize it through preview animations. For example, here the user wants to store the phone blocks in an occluded basket. She selects the auto resolution and sees that the robot can first pull out the basket, store the blocks, and push them back in. We present the resolution strategies through a mixed initiative approach. Imagine a scenario where the user specifies hanging a small poster on the right side of the wall, but the task isn't feasible due to some obstructions. The robot here can suggest an auto resolution to move the chair aside. It autonomously resolves a constraint by changing the state of another object with the dependency, in this case, the chair's position outside of what the user explicitly specifies, in this case, the poster. Or it can suggest an alternative placement that slightly modifies the instruction. Or user can simply choose to ignore the constraint and let the robot try anyways. The user can also perform virtual actions to clear the robot's path. Or provide physical assistance like stepping up to help. As a recap, we've seen that users can specify actions on virtual twins through object-oriented interactions. In fact, these object-specific properties define whether an action is feasible, such as where the book is, does it fit within the robot's gripper, etc. In the back end, we encode these object properties in its affordances, and similarly, encode the robot's capabilities as well as its hardware and software limits into object-oriented class structures. These attributes and methods allow the backend decision tree to check for feasibility. We send pass-through image captured from the headset along with robot datasheets to a VLM to automatically populate the OOP fields. These properties are encoded in the ghost objects. We instantiate them using pre-constructed 3D models and align them in a simulated environment in Unity. This alignment is done automatically via the headset spatial setup. The environment is built from a modeled scene mesh, allowing the ghost objects to respond dynamically to life-size physical boundaries. Finally, we ran a user study with 14 participants, where they were asked to complete some tasks, such as resolving dependency, choosing alternatives to resolve constraints, specifying high-level actions like vacuuming an area, and physically assisting the robot like opening the door. Overall, participants successfully issued object-oriented commands, engaged in mixed initiative resolutions, and reported that the AR visualizations were clear and accurate. NASA task load index results showed low workload in all 6 indices, and the overall system usability score was 79.3, indicating good usability. Through our qualitative interview, we found that abstraction shapes users' mental models, where participants referred to the robot when describing tasks without distinguishing between individual robot capabilities, which may obscure differences between robots and raise open questions about the optimal level of abstraction. We also observed that AR enhances expressive power, but adds learning costs, as well as the trade-off between automation and user control. Lastly, we see several limitations in directions for future work. First of all, while VLM are powerful, visual and spatial errors still occur, especially with occlusions or hidden attributes. Multi-view capture and closed-loop feedback can help reduce these spatial errors in the future. Broader testing is also needed to evaluate more complex tasks and long-term uses. Also, currently, the system requires manual configuration. In the future, methods can be used to automate the process. Real-time object tracking can also help adapt to changing environments. And finally, the system can expand from AR to VR for real-time teleoperation and utilize user interaction and outcomes to help improve robot learning. Thank you for listening.